Very good afternoon to all of you. Let's start the numerical practice on LMTD. We have studied, we have learned the theory about the heat exchanger. Thereafter, uh, we will have go through the some numerical practices so that you could be able to know how to solve the heat exchanger problem. See, earlier we were aware that there are only two kind of the problems it may be. The first one is the design of heat exchanger, and the second one is to check the performance of a heat exchanger. So to design a heat exchanger, the LMTD method is employed, whereas to check the performance of existing heat exchanger, the NTO effectiveness method is employed. So today we will go through the few numericals based on LMTD methods. So on a screen you are seeing the numerical. One is the based on LMTD, and the problem statement I am going to read it out, that hot exhaust gases are used in a finned tube cross-flow heat exchanger to heat 2.5 kg per second of water whose specific heat is 4.18 kilojoule per kg per degree centigrade from 35 degrees centigrade to 85 degrees centigrade, full stop. The gases whose specific heat is given as 1.09 kilojoule per kg per degree centigrade enters at 200 degrees centigrade and leave at 93 degrees centigrade. The overall heat transfer coefficient is 180 watt per meter square per degree centigrade. You need to calculate the area of heat exchanger using the LMTD approach. So this is the numerical problem which you need to solve. So what is the you have understood what is being asking. So there are the certain steps that standard steps you must go through for each and every numerical that you will solve in heat transfer, especially in heat exchanger. So the first step, what is the first step? The first step, you have to define the problem statement in terms of what is known. So what is known? The known is, see, hot, everything is clear. Hot exhaust gas. What is given? Which kind of heat exchanger is given here? A finned tube cross flow heat exchanger. In fin tube cross heat flow heat exchanger, the hot fluid is hot exhaust gases and cold fluid is water. That means in this kind of heat exchanger, it is given that hot exhaust gases is used to heat water. So this is the known value. That means we are knowing that there is a fin tube cross flow heat exchanger in which hot gases, exhaust gases is used to heat the water. Therefore, we are writing what is known in your own language. By understanding the problem, what is given, you should write down in your own language one statement what is known. So what we have written, in a fin tube cross flow heat exchanger, hot exhaust gases are used to heat water. Now, what is to determine? What are to find? What is to calculate? The area of heat exchanger. Area of the heat exchanger. So we have written in the next step, you should write find. So what is need to find? The area of heat exchanger. There are, in the third step, you should draw the schematic diagram. Now, this is the schematic diagram of a fin tube cross flow heat exchanger. As we are knowing that in cross flow, there are the two fluid flowing at the mutually perpendicular direction. So one fluid will move on the inside tube and another fluid will be moving outside the tube, and both the direction is perpendicular to each other. So you need to draw the schematic diagram showing all the properties value or whatever known value you have, that you should plot here, you should show here. So what is the, we have in inside tube, it is given that water is flowing through the inside tube, and outside the tube there is the gases. We know that heat transfer coefficient, heat, see there is the fin that is kept outside the fin. Why fin is used in gas side, not in water side? The answer is that the heat transfer coefficient of gas is much lesser than that of water. Therefore, the fin is used in the side, in the fluid side, which heat transfer coefficient is lesser. That's why the fin has been added to the uh, gas side, in the term and in the form of plate, and in between these two plates the gas is flowing without getting mixed. Remember here, the inside tube, the fluid water that is flowing inside the tube, the two fluid is not getting mixed, also the outside the gas flow, it is uh, uh, outside the gas flow, the gases are not mixed. So okay, so outside the gas side, what is given? The mass flow rate of the water is given, specific heat of the water is given, water inlet temperature is given, water outlet temperature is given. Gas side, the mass flow rate is not given, but the C, a specific heat of the gas is given, inlet temperature of the hot fluid, that is a gas, is given, outlet temperature of the gas is given. Also, there is the overall heat transfer coefficient is also given. So you need to show these all schematically, and all you have to show all the data like that. Okay. So now we are, during the analysis we had assume certain simplification that you need to mention. So what are uh, those simplification or assumptions? The first assumptions, that is, the first assumption is you should write down the assumptions step, all the steps that we have mentioned here, that you should write down for each and every question. If anything extra is needed, that also should written. If someone is not useful, some assumptions is not useful, then you should not write. But whatever assumptions that you are going to incorporate, you must mention during the solution of a numerical based on the heat exchanger. So what are the assumptions that, let us see. First, we had assumed during our analysis each steady state should be reached, a specific heat should not changing. That means the specific heat temperature variation is not mentioned, but we assume a specific heat as a constant with respect to temperature. Also, there is no axial conduction in pipe, and outer surface, that is the perfectly and adequately insulated. The change in kinetic energy, potential energy are negligible. Also, the overall heat transfer coefficient is assumed as a constant. It is given as a 180 watt meter square per degree centigrade. It is given, although you have to write down that overall heat transfer coefficient is constant. Also, what we assume that both fluid, tube side always as fin side, both fluid, hot and gas fluid, in the case of cross flow, we assume as a both are unmixed. So these are the assumptions that you must mention during our analysis. So next part, we are going to analyze. What are the problem? Let's revise it once again. The problem was that in a fin tube cross flow heat exchanger, the hot exhaust gases were used to heat water, whose mass flow rate, a specific heat, inlet temperature, outlet temperature were given. Also, the specific heat of the hot gases and temperature as well as inlet and outlet of the hot gases are given. So overall heat transfer coefficient were given. So by using the LMTD method, you need to determine the area of the heat exchanger. So for the analysis purpose, we are going to use, see, this is given for the which kind of the heat transfer, that is the cross flow heat exchanger is there. So we know, we are knowing that if we are interested in knowing the what are the whatever the heat that is losing that hot fluid is losing, that is gaining by cold fluid. So that heat is nothing but Q is equal to mcp mc delta T. So this Q will be equal to also m C delta T for both liquid as well as hot fluid. Also, with the in terms of overall heat transfer coefficient, what it is? What it is? Q is equal to UA LMTD. See here, UA LMTD. And LMTD for what? LMTD for the given type of heat exchanger. So here the given type of heat exchanger is cross flow. So we are going to use for the cross flow. So what is the LMTD for the cross flow? Is nothing but the if there is the correction factor multiplied by the LMTD for counter flow. Now we are going to consider, see, we need to determine first the LMTD for the counter flow as well as LMTD for the correction factor. There, with the help of these two quantity, we can determine LMTD for cross flow. So how we will determine the LMTD for cross counter flow? We will consider the cross flow as a pure counter flow. That means hot fluid as well as cold fluid are assumed as a flowing through the counter flow. So what, how we will say? We will assume pure counter flow. So we are showing the temperature variation. That means counter flow means what? The hot fluid and well as cold fluid will be moving in opposite direction. So this is the hot fluid inlet and hot fluid outlet. This is the cold fluid inlet, cold fluid outlet. So there will be the temperature difference at the inlet and the outlet. So say there is the two location 1 as well as location 2. So by taking this at particular location, whatever the temperature difference between hot fluid and cold fluid, that is denoted by delta T1, which will be nothing but the difference between the temperature outlet gas temperature as well as inlet cold fluid temperature, that is the water. The what will be the delta T2 at the location 2? What will be the temperature difference between hot fluid and cold fluid? So delta T2 will be equal to Tg minus Tw. Now we are knowing the LMTD. Since all the four temperature are given in the problem, so you can easily determine what will be the LMTD for counter flow. So LMTD for the counter flow will be delta T1 minus delta T2 upon ln delta T1 upon delta T2. So what will be the delta T1 value? Delta T1 value here it is defined as the, okay, we have opposite, this we have assumed as a 1 and this we have assumed as a 2. So it is nothing, that is not a problem. In diagram it is reverse manner we have written. Okay, so delta T1, or you can write down delta T2 minus delta T1 ln delta T2 upon delta T1. It will have no effect. So now by using this definition we have written like this one, and we are substituting all the temperature value. So say if this has been assumed as a delta T1 and this has been assumed as a delta T2. So what will be the delta T1? Tgi minus Tw naught, that is 200 minus 85, 200 minus 85, minus the delta T2 will be 93 minus 35 divided by ln delta T2 upon delta T1. The second one formula we have used. So likewise, if you can calculate, that is the very all the four temperature are given. So you came to know about the LMTD. What will be the LMTD value for the counter flow? So now we are knowing, we need to determine the correction factor in order to get the LMTD value for mixed flow. So what will be the correction factor for this? The correction factor is obtained by the plot F versus P versus with R as a, see, there is the one plot that we have learned. Before that, if correction factor, we had learned that correction factor is not correction factor of all kind of the heat exchanger is plotted through the experiment and presented as a chart in the function of two quantity P and R, and the P and R were defined as the given formula. P as a small t2 minus a small t1, capital T1 minus T1. What is the T1 and T2? T is the tube side temperature and capital T is the cell side temperature. Here tube side is cold fluid and outside the fin side is nothing but the cell side. So what is the hot fluid? So by knowing the one means inlet and two means outlet. So T2 is the cold fluid outlet temperature, T1 is the cold fluid inlet temperature, T1 is the cell side, that is the hot fluid inlet temperature, and cold fluid inlet temperature. So by inserting this numerical data, we will determine the value of P as a 0.303. Also, we can determine the value of R by definition, that is the T1 minus T2 upon T2 minus T1. So T1 is the hot fluid inlet temperature, T2 is cell side hot fluid, and this is the cell side outlet temperature, which is hot fluid, and this is the tube side outlet temperature, and this is the tube side inlet temperature. By substituting, we know the two value. Now we will move on to the graph that is plot that has been plotted. So what is the plot? You will find, you can determine from the data handbook. This is the plot of the, see, you will find from the data handbook that correction factor plot for single pass cross flow heat exchanger, both fluids and mixed. See, if one fluid is mixed, another fluid is mixed, that has the separate plot. Here what we have assumed, well, we have assumed as a single pass cross flow exchanger in which both fluids are unmixed. So there is the, this is the plot. So this is the plot. So that plot you can see, this is given for the cross flow. This is the one side and the which is the perpendicular to each other. Now go to the plot. What is the plot? Here in the ordinate side, that is vertical plot, correction factor, horizontal plot is P, and there is the another quantity that is varying, that is R. What we have calculated P and R? How much calculation we have done? We had calculated P and R as, see here, P as a 0.303 and R as a 2.14. So by finding this one, where it will lie? 0.303, that means somewhere in this location, and R is the 2 point something. So R2, see, you will have to draw a vertical line at this line, as well as you will have to draw a line in this shape. That means somewhere 2 greater than 2 line, that is left side. So if the 2, this one is the vertical line as well as this line, the point where it cut down, that will have to, you have to mark and draw a horizontal line. So whenever you draw a horizontal line in the this line, vertical line, wherever it cut down, that value will be given as a correction factor. So by doing this, so we got a value of correction factor F as a 0.92. Simple, very easy. It is, you can determine by reading from the plot. So it is 0.92. Now we had determined the LMTD correction factor as for the counterflow. We came to know about the LMTD as well as correction factor. So we had Q value. Now we can, what will be the Q value? The heat loss by the hot fluid or heat gain by the cold fluid. So cold fluid, we have mass flow rate is given, C is given, delta T is given. So by using that energy balance, Q is equal to MC delta T, we can determine the value as a Q as a heat received by the cold fluid is as a 522,500. This much of the watt. So this watt, this much of the heat you know. So this is the heat transfer that is needed for the the heat transfer that is taking place from the cold hot fluid to cold fluid. So to have this much amount of Q, what are the surface area that is needed, that you need to determine. So we are going to employ the formula Q is equal to UA LMTD cross flow, and we are knowing that Q is nothing but UA. For the cross flow, we are knowing that correction factor multiplied by LMTD for counter flow. So this counter flow we have calculated some LMTD value. If we had read out from the chart, U is given in the question, Q we have calculated. So by substituting this one, area needed for this Q amount of heat transfer, we can determine by using the formula Q upon UF LMTD for counter flow. That means the 522,500, by substituting this formula, we got to know about the 37.89 meters square. So this is the area of the heat exchanger that is required in the case of cross flow to have the Q amount of heat transfer. So this is our required answer. So 37.89 meters square. So in this, by doing this numerical problem, we know how to use how to calculate LMTD, how to, first of all, how to solve a numerical problem, what are the different approach. So what are the different approach are? First, you need to determine what is the known value, and you have to write a statement in terms of your own language. Thereafter, you should write the what value, the what is the find, what is in problem, what is needed to find, that you should write down. Thereafter, you need to draw the schematic diagram, and you should put all the data that has been given in the schematic diagram, say mass flow rate, temperature, specific heat, overall heat transfer, whatever it is given, that you should show on the schematic diagram. In the next step, you should write down, you should list out all the assumptions that you are going to use during analysis of this numerical problem or a particular numerical problem. This is very, very important. If you will write the assumptions, that means it is understandable, that one can easily understand that you have understood the numerical concept very well. So we have listed out these all assumptions you should write down during the practice. Thereafter, we will come on to the analysis. Since this is the since this is the cross flow heat exchanger, so cross flow, in the case of the cross flow heat exchanger, what you will do in the case of cross flow heat exchanger, that we do not have any LMTD direct formula, but we are knowing that LMTD for the cross flow we can determine in terms of LMTD for corresponding to the hot fluid, corresponding to the counter flow. So first of all, we will assume it as a counter flow, and we will determine the LMTD value. So LMTD value for the cross flow, we can determine the temperature versus length diagram. So in the abscissa, we have presented the length of the counter flow. In the vertical, we have presented about the temperature. Now for the counter flow, or whatever the, whether it is counter flow or parallel flow, the formula will remain same. And by substituting all the data value, we can determine the LMTD temperature. See, in the case of LMTD, in the case of designing of new heat exchanger, you will be knowing all the four temperature. That means hot fluid inlet outlet temperature, cold fluid inlet outlet temperature. So if you are knowing somehow the temperature of correction factor, then you will be able to know the LMTD for the cross flow. So how will determine the cross correction factor? We were knowing that correction factor is obtained by the use of plot that has been plotted from the experiment. From the experiment, it has been plotted as a graph. That plot we can show that in the, you can find here like this one for the cross flow. See, it is written in the bottom that correction factor plot for the single pass cross flow heat exchanger, both fluid being unmixed. By knowing the P value and R value, the definition of R is mentioned here. By determining these two R value, if we can determine a particular point, and by determining that particular point, whether it will lie here or here or here somewhere, you can determine the correction factor. The correction factor, the determining from the of the value of the correction factor from the plot, you can determine the LMTD value for any kind of heat exchanger. Say here LMTD for cross flow. Now you came to know about the LMTD value. Now you are going to determine what is the amount of heat transfer that is taking place. So we had used MCP dt value, and you came to know that whatever the heat amount is, by substituting the data, you know the 522, 5000 amount of heat. Itna what is need to transfer. So Q is equal to UA LMTD cross flow. By using LMTD cross flow, we are knowing the F into LMTD for the counter flow. U is given as we have mentioned it as a constant value. So this is U, and Q you are knowing. So we came to know what area it is needed. Hence, this is the answer. So we learn how to solve. So if you have any doubt, you may ask, please. If you have any doubt. So I hope you understood. So now we are going to, we have learned the numerical practice. We have learned numerical. So anyone have doubt, you can ask from this. If you have learned, if you have any doubt during the solution of this problem. Okay, so all of you have understood well. So we will do few more numerical practice like this one. You must do at your own the same process, the same solved problem. You should practice 2 or 3 times so that you could able to understand what process, what are the standard process or standard steps, how we need to. You should understand the uh, key point. Okay, any doubt? Anyone has doubt? No one.